Hi guys, today we're going to continue with the rate of reaction, and we're going to discover more of how to determine the order of reaction to write the rate law or the rate equation. Now look here on the syllabus, it's very important that you understand this part. It says here, construct, right? Again, construct rate equations. We are still on rate equations, right? I put it smaller, it's a bit big. Okay, right? From concentration time graphs. Now, very important, this word concentration here, right, is mainly of reagents or reactants. You can put products, but normally they won't give products. Because products is quite, because why? Because the rate equation, the rate, right, is equals to K, concentration of what? Reactants, A power of A and B and so forth. So all these are reagents, reactants. So you don't talk about the concentration of the products that will control the rate, but the concentration of the reactants. So here, normally, okay, you use concentration of your reagents. You have to derive this rate law. Okay, so it's from experimental data. Now in experiment, you of course measure what? The disappearance of your reagents again, with of course time. You can measure the rate by appearance of products with time. You can, but that will not help you to get your rate law. Okay, so it's always experiment data, okay, of concentration of reagents against time. So we have to talk about initial rates. Why initial rates? Because we actually can know what is the concentration of your initial reaction as of all your reactants, because you prepare it, okay? And of course, two methods here. One, of course, is graph. Okay, here I'm going to put blue just to let you see the difference. I'm trying to hurry. Okay, 3:30. Okay, here, blue. Now, two ways. One way, of course, is using the concentration time graph. Okay, one way. Second way is called half-life method. Okay. Half-life method 2. Half-life method, normally we use it for first order reaction. You will see after why. I'll explain the theory to you. Okay, so here interpreting experimental data again in graphical form, including concentration time graph. Okay, and one more called the rate concentration graph. We're going to convert this into this. Okay, so you can see this is a starting point, because this is where you use all your experiment data for to plot the graph. It's the first graph, it's the second graph, if they ask you, okay? So you can see this. Now let's go to where we stop. Now, yesterday, we actually stopped in this, or the other day, not yesterday. I did this yesterday, that's why. Okay, we stop with this reaction here. Remember, right? Iodine plus propanol plus acid, right now. So we measure the amount of iodine from the volume of your thiosulfate. This is proportional to the concentration of your iodine. Not equal, but proportional. Okay, or it's equivalent to the moles per dm cube. Okay, right? This is concentration. That's why this is reactant. So from here, experiment 1, experiment 2, we come to this conclusion. And I'll put it here already. So experiment 1, you can see here 0.02 is all, okay? So the rate is this one here. So we say, well, the rate is constant. Why constant? Because we plot a graph, remember, right? This graph here. Now remember, this part here is proportional to what? Concentration of iodine. Now this is very important now, okay? That means this one here, this reactants the order can be deduced from this graph. You cannot deduce the order of propanol from this graph, but you can use it to deduce the rate or the order from the graphs. Like two graphs here, you can use two graphs from this method now. Okay, now here is how you determine it. Okay, now let me show you. Okay, now here I should have told you yesterday already. Now here I've from the first graph, okay, from the straight line graph, I determined that iodine is what? First order. Okay, because why? The rate don't change even as the initial concentration of the iodine changes. Rate is constant. right? So the rate don't depend on concentration of iodine, which means that however much iodine you use, you always get the same rate if everything else is kept constant. Experiment 2, we keep the same iodine concentration, okay, the H plus concentration same, and we double, okay, double the concentration of your propanol. See, the rate doubles. Now there's a way to explain this. Okay, later we go and see how the mechanism goes. Okay, if you increase the concentration of propanol by 2 times, okay, increase by 2 times, the rate also increased by what? 2 times. That means you can say, well, from here you can say that, well, the order with respect to your propanol order with respect to propanol is first order. Why? Because y equals to mx plus c, okay, right? So c is constant, equal to 0, so y equals to mx, okay? So if x power 1 here, so when x changes, let's say I put y equals to x, okay? So when x is 1, y is 1. When x is 2, y is 2. See now? See? If I increase it by twice here, right? Increase x by 2 times, right? Y is increased by 2 times now. X increased by 3 times, y is also increased by 3 times. So it's proportional. That means it's power to 1. This is the first order. Also can see here from experiment 1 and 3, right? This is constant. This is constant by double the H plus times 2. The rate also doubles times 2. So again, the power with respect to H plus also power 1, first order. Which means now to say that what? The rate equation is equal to K, iodine concentration, power 0, and propanol concentration, right? The power is what? 1, and your H plus is also 1. So this is called the rate law or rate equation, okay? I'm going to show you the second method to determine rate, okay? Now here, as I said, they actually ask you the method. Later in your A2, they will ask you the method. All right, now here, I will go to that first, okay? Calorimetric, use a calorimeter. Here, right? Now in calorimetric analysis, one of the reagents, at least one of the reagents, one will do it because the other one will interfere, see? Must be colored, okay? So can be the reagent, also the reactant. This is a reagent. Okay, so same thing, you put bromine into your methanol acid, and your acid here, H2SO4, whatever. The 3 of them will start to react. Okay, and of course you can measure the disappearance of bromine 2 by color. So as I told you here, is I got download for you here the calorimeter. This is a calorimeter. Basically, there's a light source here. It goes through a lens, concentrated, and here actually is a filter. This is a filter actually. Okay, it's a filter. Okay, where I would choose the color. The color must be complementary to the color here. For example, if bromine here, right, is orange. Okay, the complementary color is blue. So I must have a blue filter here, blue filter. Okay, if it's yellow, then I would choose a, if it is blue, I would choose a yellow filter. Okay, so the filter must be complementary color to this. You will see this later as you do in the biochemistry. Okay, so this is a calorimeter, and of course, as it passes through here, right, and the amount, if the concentration is high, that means if the concentration of your orange is high, okay, it will absorb all the blue. That means nothing passed through here. That means absorbance is 100%. Okay, so if as the reaction proceeds, the concentration of your bromine will decrease in, right? And so more light will pass through, more blue light will pass through, right? And as a blue light pass through, it will record more here. That means absorbance record more here, absorbance become less and less. So at the end, it becomes very small absorbance here. So you can see from here, you can plot a graph like here. Okay, so in the beginning, the absorbance proportional to the concentration of bromine here. Absorbance can be measured like here. You can see it gives you a value here. Okay, here. This is the value. This is absorbance value. So in the beginning, it's very high value because high concentration of Br2 hasn't reacted with now. So as it reacts, this value will decrease. Okay, it will decrease. It shows you the amount of bromine has decreased, and that's why you get this data here. See, 0.01, 0.09, and so forth until 0.0013. So as time goes on, the amount of bromine it will decrease. It means that there's a decrease in the concentration of your reactants. Of course, now you can plot a graph. Okay, so a graph is plotted with what? Concentration. So a graph like that is plotted. Here is a concentration of bromine. Okay, in terms of absorbance. Okay, it's mole per dm cube. Okay, from the absorbance value. Absorbance value. Okay, against time. So again, it is concentration of reagents versus time. Now, in this case, all the time for your practical, for your experimental data is always concentration of reagents. Okay, against time. Now, for this graph, there are three types of graph. Now, let me show you the question that come out because of this 53. See here? Now, see, the following just show three ways the concentration of reagents might vary during the reaction. This is per time. See, reactants and time. Reactants and time. Reactants and time. Now, if the reactants plot against time, of course, at it is the highest point where you start with 0. Right? That means now you know this concentration. Why? How come you know this concentration? Because you plan it. Right? You make it, isn't it? You put how many grams inside so you can calculate. So this is a known value. Right? As time increases, of course, you can measure the concentration by what? You measure it by two methods. One by what? Titrimetric. Second by what? By calorimetric. So you can measure in experiment two ways to measure the concentration of your reactants. Like we titrate against thiosulfate to find the concentration of your iodine. Here we measure the color from the calorimeter to find the concentration of your Br2. So if it's a straight line down here, we say, let's say this is iodine here. Okay, so straight line here means that the rate don't change as the concentration of iodine decreases. That means that it's zero order. It's zero order. Okay. Now, for the one that we just plotted, well, it can get a curve. See, of course you can start from here. You know, this is the initial. Okay, you can start from here, right? So it goes like this. Now remember, for this graph, for reactants versus time graph, for a curve you can get two types now. Okay, two types. One, of course, now this one, of course, is the first order. So if a curve is first order or second order, it's hard to tell unless you do another graph, which I'll tell you later. Okay, so if the third type of graph is a horizontal graph, now this is a very tricky graph in the sense that it tells you nothing except that one of the reactants here, okay, which you use is in excess. Okay, so it does nothing but the reactant here is in excess. For example, got 1,000 men and 3 ladies. You want to get married time, okay, in first year one get married, second year one get married, third year they all get married. After 3 years, I mean, you can measure the rate at which the ladies get married. But you want to measure the men, you know, it's hardly any change. From 1,000 it goes to 997, so the graph don't change much. For the ladies, it'll be 3 here, it'll be 2 here, it'll be 1 here, and of course, zoom. Okay. For the men here is 1,000 here and 997 here. It's almost a horizontal line. So if it's a horizontal line, that means that reagent here is in excess. You don't say anything. So in this case, there are actually 3 kinds of graph, like you can see here. Now here, okay, so propanol here, right? We can see down here to tell you that propanol and H plus is first order. Okay, so in this case here, it'll be A. Propanol is A, okay, the type of graph. And of course, acid is also A. Iodine is, of course, is B lah. What's the straight line graph? Okay, right? So now I show you here again the type of graphs you can get. See, these are the things you have to know before we proceed now. This one here, this remember is a concentration in mole per liter for DNQ. Here is the concentration of reactants. Okay, I want to put reactants here. Okay, what's the time? This is the main graph you would get after your practicals. So if it's a straight line down like that, okay, straight down like that, this would be a zero order. Zero order. Now it's a curve. See the green line and the blue line. These two are curves here. They, of course, the green line here tells you it's a first order lah. Of course, you won't know. Okay, the second one is the second order. Now you won't know from just the graph because it's both are curves. But you can actually determine from one more graph, which you do it after your experiment. Okay, which you actually have to plot. You actually have to determine the rate at every initial concentration, which means at this point here, let's say I do the green, okay, I have to draw a tangent here. Okay, right? To find the rate here, because why? This theta here, tangent theta is equals to, well, this concentration here to here, which is about, well, 75.00 times 10 to the power of -3, right? 75.00 times 10 to the power of -3 over the time. Okay, here's 5 seconds, here's 2.5, let's say it's 1.3, okay? So this is the rate at this concentration, okay? So then I plot the graph, okay? Right? This is the rate right at here, okay? So and then I plot another graph here for this concentration, which is about 75.00. Okay, now I have to draw another tangent at this point here. See? Yeah. So I find the tangent again, and I now plot the graph here. Okay, at this concentration 75. Sorry, 75 here. Okay. It's all the range. Okay, like here. Okay, and subsequently here, that means every rate. Every change of concentration here, I get a rate here, and I get a straight line. So a straight line means what? Y equals to mx. Okay, go to 0, isn't it? So c is 0. So y is a rate. Okay, m is the slope. X, of course, is the concentration. Okay, of x here. So because the straight line graph is a power 1, so straight line always prove a point. Straight line graph is the best way to prove a point. Curve very hard, like these two curves. This second order is first order. Hard to prove it, but straight line will prove. Okay, so straight line means that it's first order. Okay, and of course, if a curve like the blue line here, right, this blue line here, right? If you plot similarly for all the slopes, the tangent at every concentration here, you get a curve like this. Of course, it's going to start from 0 here. This, of course, equals to what? Y equals to ax squared. Okay, right now, let's start at 0. So if y is the rate, equals to a is a constant, this is the concentration of this is b here, power 2 there. That's why it's second order. Second order. Okay? So it is how you use graphs. So we are only asked to use determine 0 order, first order, and second order. Now this is from second order, okay? This is from a rate versus concentration. This graph you get from subsequently from this first graph. This is the first graph you get from experiment. Okay, so normally this graph is the one that you will use a lot in your exams. I'm going to show you how they use it. Okay, now first way, of course, here is I told you normally if it's a curve, we can say that for your A levels is a first order, but you can prove it by a simple method, not by drawing all the tangents at different concentrations. Simple method called half-life. Okay, now I'm going to show you well, the theory quickly. It's not very important to know the theory. You just need to use the concept. Okay, now here, okay, for first order reactions, right? That A goes to B and C. That's at time 0. I'm going to put here A goes to B and C. Okay, right? At time 0, okay, this is, let's say, A moles per m cube. Okay, right? And this is 0 and 0 here. At time t seconds, X have reacted. So X is from here. Okay, so remember this is an elementary step, which means one step. A goes to B and C. So here will be A minus X at time t. So this is the initial concentration after time t. Okay, so I can say that, well, dx increase in products over time is proportional. So dx over dt is proportional to the concentration of A minus X, the power of 1. The power 1, because we assume this is elementary, it means 1 here. Okay, right now. Okay, 1 here. So 1 here. So if you look at it carefully here, right? If you, well, this maths, okay, you bring this down and you bring the dt up, okay, right? And then you integrate both sides. You get minus log base E A minus X. You can do it yourself after, okay? I'm just showing you how it's done and so on. Okay, K dt becomes T, but it's a constant because you integrate. So then to find T, you put T equal to 0, so X equals 0, because at time 0, you get nothing, no, there's no reactions there. So your C is equals to log minus log E base EA. So you substitute into here, you get this equation here, right? You bring this one over to this side, or whatever side. So KT is equals to this one here. So again, you rearrange this whole thing, right? You be KT, should be KT equals to, right? Remember you bring over this this side, okay? You just will log base E A over what? A minus X. That's not, okay? So you bring the T down with K is equals to 1 over T, and log base E A minus A over A minus X. Okay, so you change the log E to base 10, you put 2.303, right? Now, so this is a final equation here, this part here. Now then you say, well, half-life, what is half-life? Half-life, it doesn't mean half the time, it means half-life. Half-life means here half-life means the time taken, right? The time taken for half your original concentration to goes to half. Let me see, this is start from 10. Okay, this is initial concentration. It goes to 5. Okay, this is called a half-life. 8 goes to 4. This is called a half-life. Okay, in half-life, see the half-life thing here, right? See, the half-life is equal to a constant. See, 0.693 over K, and K is only dependent on the temperature and the type of reaction. So if one type of reaction, temperature is fixed, it means half-life is the same. So for first order reaction, half-life is the same. That means you can prove 2 half-life the same. 2 half-life will always disappear when I need it. 2 half-life is the same. Okay, the half-life same. Must show 2. Okay, that means it's first order. Now we will look into this now. Okay, I talked a lot already. Now I want to show you how it's being done. Okay, so now I'm going to take a question here. Okay, the first question, of course, is we're going to look at 51. Right, 51 here. Right now, okay. Before that, I went through this the other day, so I thought maybe I'll do it again. Right now, here remember now, I told you here. See the ester 4-nitrophenol ethanoate hydrolysis in alkali solution for the equation. Okay, now here, remember, I told you that this is by what? Calorimetry. Calorimetry. That means you use a calorimeter to determine the rate, see, to follow the rate. Okay, now I told you here this is colorless, but the product here is yellow. Now you can either use a reagent or product to measure, right? they actually, in here, they actually have to convert the product back to the reagent. I won't tell you how, but it can be done. Okay, so here it says, suggest, they tell you that this is they want to fool you, see? So this is the product. So you actually measure the product. That means the increase, there'll be increase in transmittance, or there's a decrease in, or there's a increase in absorbance, correct? Okay, suggest and briefly describe an experimental technique to study the rates. Remember I told you, I didn't put a thing here. Hold on, 0 to 0. Okay, here we are. Right. Now, remember I told you that there are 5 points here, right? So the first point you need to say is mix the solution. Okay, it means this, the ethanoate and your NaOH, now these are both are the reactants. So you must say it, okay, and mix it, right? Do not allow titration of NaOH. You cannot use, right? It means you use what? Calorimeter method. Now you must tell them 2 things. Now here it says all, see, concentration of the ester and the volume vector. That means a known concentration and a known volume of both of these are important. Okay, so there's 2 marks here. Mix the reagents with known concentrations and known volume amounts. Okay, 2 marks here. Then place it in the calorimeter with the right filter. I told you, okay. So calorimeter with right filter, and then take the time. And every time, in regular intervals, measure the absorbance. Okay, normally it's the absorbance, how much is being absorbed, the color. Okay, which will proportional to the reagents or the product. So there are 4 points here, 5 points here. Okay, regular intervals. Here will be regular intervals, and take the absorbance here. So 5 points here. I'm going to show you how I wrote it here. Right, you can see here how I wrote it down. You can, but see, when you study, you need to rationale. Why so? Okay, here, known quantities. Proceeded on the first one. Known quantities. That means here with the volume. Okay, volume 50.0 cm3, and concentration, the molarity. Okay, like I told you, like iodine is 0.02 mole per ml. Okay, of here is of these are the 2 reactants. So 1 mark for known quantities and concentrations, right? And 1 mark for the 3 reagents here are mixed. See, and time started. Okay, so this 2 marks already here. And place the mixture in a cell. This is a cell, actually it's called covate. Okay, so it's a small cell, and then put into the calorimeter, right? So this 1 mark here. And at regular intervals, what do you read? The absorbance. Okay, calorimeter here with the see, with the blue light here with the filter here is 1 mark. At regular intervals, 1 mark. Take the absorbance 1 mark. 5 marks here. Okay, so from here, these are 5 points here you can score just to write out the experimental technique. Okay, so here you can see how they should, see, mix, right? Mix the reagents 1, 2. In here is 2 lah. For bromine and methanol acid and acid itself, there are 3. Okay, with of known volume and concentration. Okay, right? Okay, mix it, and then, right, you see it's known now. Okay, and then start the timing. Put it in the calorimeter with a fixed filter. Of course, here you can put a yellow filter or blue filter. Okay, and at regular intervals, here is time. At regular intervals is the best word here. Okay, take the absorbance, increase or decrease the absorbance. Right, after that, plot absorbance. The keyword is plot and absorbance. Plot the graph of absorbance. Why absorbance? Because this is proportional to the concentration of your reactants against time. So this is the key graph, the first graph you will use. Okay, so now that is of course 4 marks or 5 marks, right? So now here I'm going to show you. See here, if you look, you want to plot this, you can try it. Okay, absorbance of Br2 against time, and then later, well, I done for you to at every point, at every concentration of Br2 here, I found out, I did the gradient and found the rate here. So if you plot now, okay, rates against concentration. Remember, it's always rate and concentration. Okay, rate. So it's his rate against concentration of Br2. You will get a straight line graph. It shows you that is first order. Okay, right? Okay. Now, secondly, okay. Now let's look at one question. Okay, right? This is 51. That's not a question there. 51. Okay. Now here. Okay. So the reaction rate was studied using two solutions of different hydroxide ions. I'm going to throw you the deep ocean here. Okay, with a tough question. Not tough question. It's everything inside here. Okay. Now run A and run B. That means there are two experiments. Okay. Now here the experiments that you're measuring the ester. Okay. Of course, the ester here is colorless, right? Okay. But there's a way to convert the products to concept of ester one. I won't tell you how, but don't worry about it. Okay. So you get this one here. So they say you don't care, no. In exam they give us, you just do that. Okay. Here, of course, is the beginning. Okay. This is initial. This is called the initial concentration. Initial what? Concentration or what? Of your ester. Remember, it's ester. It's not for hydroxide, Okay. And of course, you plot this against time. So run A. Run A means that you do it first. You imagine the B graph is not there. Okay, which means for here, right? Okay, ester here, you want to put here. Here, ester is how much? 0.001. Okay, so here, I say, here, run A is 0.001. Okay, 0.01. You know it, right? Why? How come you know it? Because you prepare it one. Okay, and hydroxide is 0.2. So it's rather than excess, so 0.2, it's 0.2. Okay, so after doing this one, then that's the first graph here. Okay, I told you already, because it's not a straight line graph, that means it cannot be zero order, right? Now, because the slope at any point here will tell you that it is not a straight line graph. It's a straight line graph, that means it's only one slope. As it's going down here, it means there's many slopes now at every point here. So how can you prove it's first order, second order? Very simple. As I said, you use what? Here they didn't ask you to plot the other graph of concentration versus, rate versus concentration. It's too hard to do it. So here you have to use half-life. Okay, now I'm going to show you the other one here. I did it here already for you. So to save time. Okay, now here is the, okay, now this is the same thing here. Okay, now how to find the half-life of run A? So this is my original, okay, the first half-life. Okay, the concentration of 0.001. To find the half-life, okay, from here, that means for it to decrease to rate until half this 0.0005. Okay, that means here. That means from here, this point here, to this point here. Okay, that means it's decreased this amount. Half of it, half of the original concentration has been reacted. So this from here. So the time taken from here to here is called a half-life. T half. And how much is it equals to? It's equals to 20 minutes. 20 minutes. So I put down here. For this concentration, this is the initial concentration. Okay, initial to final. Half-life is equals to, this is how I put, okay, 20 minutes. Now I need to have 2 to show that it's constant, isn't it? So number 2, I can see well from 0.0005, of course easiest goes at 0.00025. It means from here to here. Okay, so from here goes down to here. here, see here. So the time I start from here. I start at 20, go down to 0 is 0.00025. Okay, 25. Go to here, and here. So it's 40 here. So 20 to 40. It's the time taken for it to go from 0.0005 to 0.00025 now. So again, what's half-life here? I found it to be 20. This is from the graph, isn't it? So because it's constant, right, I can say, well, right, okay, that means the order with respect to, remember, it must be here. Because this graph is for ester, to ester, put a concentration is equals to what? First order. Okay, now, this is the simplest. Half-life is the simplest to do. Okay? But then they also ask you to find the order with respect to OH minus. So they plot another graph here. Okay, now the second run is to do it. Okay, run number 2. Let me go to here. Here. Okay, for run number 2, run B. Okay, do an experiment. All right, now here they kept constant 0.001. How do I know constant? Well, here you can see what, okay? The same experiment here. See now, ester is kept constant now. See here? I put red ink. Okay, see now, this is the original. For run B, same. I know it because I prepare it. Okay, but what's different about run B? I times 2 the concentration of your OH minus. So here is 0.4, sorry, 0.4. See, just like your iodine propanol acid, same thing, I double it. So it's a double it, of course the rate will be faster, faster. It will disappear faster. Okay. So now what can I get from this? You know, all I know is if I find a half-life for B, also it will be first order ester. So what I must do now is I ask you to plot to find the initial rate at both of this A and B. That's what they normally ask you to see here. They actually ask you to see. By drawing tangents on the graph, measure and calculate the initial rates of reaction during the 2 runs. Why initial rate? Why initial rate? Because you know the initial concentrations. Okay, of what? Of both the ester and the OH minus. Right now, because the first run is 0.0, I forgot, 0.00200, 0.001. This is 0.2. The second one is 0.001 and this is 0.4. You know the concentrations. So what can you do now is to find the tangents at initial. That means what I must do is draw the tangent here. Now, let me give you a good advice. This is mathematics. Okay, I'm going to put green color here. See, I need to find the tangent at this point for both the graphs. So normally what I ask students to do is to extrapolate the graph like that. Not this one A. Okay. So now, then you put a ruler here to draw the tangent. And the tangent you cannot use the space. You must find the tangent through here. Okay. Now I've done one here to make it easier for you. Okay, here's now. Okay, now the red line here shows it the tangent of the red line here, the tangent. Okay, the tangent for run A at initial concentration. See now, for run A, because the two lines here are different. You know? So this is this will give you the red line here. Okay, stop it here. Here's about 816. Okay, right now. Okay, so I can find the theta here. Okay, so the tangent theta here, I found it to be the slope here for run A. The whole thing here is 0.001 to here is 0. So the whole thing is 0.001 over 16. Okay, right here. So this is the slope. Okay, now again, now for run B, again I must find the at initial concentration 0.001. Okay, I must draw a slope nicely, use a ruler. As I said, if I go back to this part here, I would have to extrapolate. I'm going to use blue color. Okay, blue color. I'll extrapolate this graph here. and I use a ruler and I see now, and I find again my alpha whatever lah, okay, and I did it here to let you have a look now, the blue line here, okay, which I done nicely here. Of course, use the computer. Okay, so the slope again is 0.001 plus whole length here over time is about 8 around there. So you get this one here. So I got the two slopes. Now I convert the whole thing into a table. Now this is, I call it the mother of tables. This table is a very important tool for determining the order. Normally this is given. This diagram is the key if you don't use graph method. This one will summarize everything that your experiment did. So I got run A, run B. Okay, initial concentration of ester is this one here. Okay, 0.00. The 3 should be here. Very bad typing. Okay, 0.01. Why? How do I know? From the graph. See, 0.001 initial concentration. Okay, and what's the concentration? Initial concentration of OH minus? I also know. They give to me. Okay, they give to me here. See now, here, 0.2. Okay, so I know. So I put it down here, right? Initial concentration, this and this. I also know the initial rate. Of course, this should be initial rate. Okay, which is this one here. Remember the rate is more per dm cube per minute, okay? Right, because it's in minutes here. So it's 0.00006, okay? Now run B, of course, I know again the initial concentration, which is what? Again, 0.001. Why? Because I prepared what? From graph here, isn't it? What about the initial concentration of your OH minus? Also I know, because it's given in the question. 0.4. Okay now, so these two know, I now can also know, put my rate inside here. Now, from the graph, I know the order respect to ester is first order. Okay, from the two graphs, I can put it into this thing here, this table here, and compare. So when this is held constant, okay, no change. Here I times 2. When I increase this by 2, what happened to here? Also increase by 2, is it? Now, if you don't believe it, you can do what I told you. Use the ratio. Remember, rate, okay, is equals to K. If you don't know, this is the general equation for what? Let's say A here, for the rate equation, OH minus here, B. So if it is run A and run B, okay, so rate A equals to K. K is constant for a given reaction and for a given temperature. Okay, ester, of course, we know is 0.001. Okay, and we know it's already first order. But doesn't matter, you don't know, never mind. No, you can still put down because it will cancel off. See now, okay? And of course, OH minus is what? 0.2. B. Rate of B, ratio method is the easiest and the most effective, I guess, rather than arguing out. K, constant of this is 0.001. Power A over 0.4 power B. See, this one will cancel off. I put red, so it's easily distinguishable. Red. Okay. So I can cancel K, same. I can cancel these two. Even though I don't know the what, I can still cancel it because it's the same. So I get rate A, which is equals to 0. What? 0. Let's check it again. 4 zeros. 0.0000625 over 3 zeros, 0.000 what? 125. Okay, you'll find that this is equals to half. So this also is 0.2 over 0.4 B, the common in this indices powers. So it's 1 over 2. B is 1 over 2. That means B must be equal to first order. Okay. So this is how you use the same graph, but two graphs here, right? of different concentrations, you can use the initial slope or initial rate to find the order respect to the other component here. Okay, so this is how you do it, right? Okay, now next, of course, is the question here asks you to calculate the K. I'm going to once and for all. Okay, so initial rate, you put this down here. From your results, calculate the overall order. Okay, respect to OH minus 1. Okay, which means it's first order. Okay. From the curve of B, determine the overall order. Okay, from your results, calculate. Okay, right here, ester, of course, first order. How do you arrive in D? Okay, now part 3 here. Okay, for ester, you want a half-life. No, half-life. Half-life is constant. You must put down now. Okay, like I show you here. From what to what? The other one here. See? Okay, this one here. Okay, the best, of course, is to this one, but they don't care. You know, actually, when you put this 2 times, enough already. Okay, right? I think it's here. I put down here, if I'm not mistaken. Half-life. Okay, here. See, half-life. Okay, half-life. Okay, it's about here. See? Okay, half-life is here. Right? See, because of half-life is here. Because sorry, no, it's one here. Wrong one. Wait. Doesn't matter. Okay, half-life. Right? So because of half-life. Half-life is how much here? I did it here. 20 minutes, sorry. Not okay. Half-life will be 20 minutes. Okay, half is constant. Half-life is equals to 20 minutes. Okay. Now you have to show 2, as I said here. 2 of them, right here. Show 2 of them. Okay. This is how you show it from the initial concentration to final. Initial to final. Of course, you can use 0.008 to 0.004. Okay. So 0.000 or 3 correct here. Okay. It will also give you 20 minutes. Huh? As long as this is half of this volley already can. Okay. So this is how you determine by half-life. Now here, say that after you write the rate equation. Okay, simple, isn't it? So you put rate here equals to what? Rate equals to what? I put the K. No? Okay. K, of course, here will be your ester. You don't have to put the whole formula. You put ester power 1. Better put power 1. Of course, OH minus here power 1. Okay. Now here, of course, here use your rate equation and initial rates to calculate a value for the rate constant. This fellow here, I'm going to put red color. Okay, to calculate K. All right, use the initial rates. You can use any one. So let's say use the first one here. Okay, I'm going to go to here. Right, it's easier here. So remember here I've got. Okay, remember this. I get what my rate is equals to K ester power 1 OH minus power 1. So rate, you can use either this or this. Up to you. Up to you one. Okay, initial rates, okay. So let's say I use the bigger one. Okay, it's 0.0000125. K, I don't know. Ester will be what? This one here. Okay, and this one here. So the relevant concentration you must use. Okay, you can use any one you like. Okay, with 0.001 times power 1, 0.4. Okay, K, of course, you can calculate. Okay, a value here. Use calculator. Now they also ask you for the units. Now, how do you use the units? I'm going to rub this off because it's bothering me. Okay, now units is very important here. You must understand now the units of your rate is the key, right? I'm going to put down here green color. Okay, and how do you find it? Very simple. Now, rate here, what's the unit for rate? Remember, right? I put down here already, right? Mole per minute is not. Yes, sir. You can put per second, you just change it if you want to. Okay, mole per, okay, so here, so K, remember K is equals to rate, right? over the concentration of your ester power 1, concentration of your OH minus power 1. So actually it's equals to, put on right here, mole per dm cube per minute. Over here, what's unit for ester? Mole per dm cube. And here power 1 is it? So power 1 here, mole per dm cube. Power 1? Power 1 is here. So it's something you can cancel off. So what's the unit for K? Very simple. So it's what? You bring this up here. So it's mole minus 1 dm cube minute minus 1. Got it? That's why you need to actually know what is the unit for your rate. It's always constant. It's mole per dm cube per time. Can be second or minutes. No, per time. So this is fixed. So if you know that, then everything is simple. Okay? Right. Now, let me show you another question. Tricky question. I think we have time for just one more question. Okay? Page, well, let's see. 2 more questions. Okay, 59 or 59 first. Okay. Now here is a very simple question here. Right? Remember now this reaction here, the mechanism I will do, well, I think next week probably. Okay. So this is a three reagents of hydrogen peroxide, I minus and H plus. Now this is the mechanism. We will do this later. Okay, don't worry about this. Okay. Now here's a general equation which I talked about last week. General rate law, okay, and so forth here. Right. Now, so here they ask you, okay, a study was carried out in which both the H2O2 and the H plus were kept constant. Okay, remember? You can see here this is very much excess compared to the original concentration of your I minus. Okay, 0.05, 5 times more, so 50 times more. Okay, 50 times more. Never mind. Okay, I minus here. You can see it's a curve, right? Concentration of reagents versus time. Okay, remember if it's a straight line graph, it be 0 order, isn't it? Curve can be a first order or a second order. So how do you prove normally it's a first order? Okay, so now here they ask you, right? To gain full mark, blah blah blah, calculate the initial rate of this, okay, and state its units. Okay, which means what? Initial rate means what? The starting rate. Initial rate here means here. So again, you have to find the slope. I told you before, to find the slope here, you need to be smart enough to extrapolate the graph, right, to get nice curves. Then of course, I'm using blue color here, right? Use a nice ruler and draw a nice tangent here. Okay, whatever, okay, and then tangent here. You cannot use anything out of the grid here, the scale here. You must use the values here and the values here. Okay, to find the initial rate. Cannot. Okay, that's the first part here. Easy, isn't it? Right? Right? Now then here. Okay. Okay, in the units. Okay, of course, rate. What's the units? What? Mole per dm cube per. Now here is minutes or seconds. Okay, seconds. Okay, per second. Okay, this one you get from the slope. See, they are 1 units as well. Rate. Use half-life data from the graph to show direction. To show direction is first order. So here's to calculate the rate. Here's first order. Okay, they say use half-life. Very simple, isn't it? So you can. I mean, you must have 2. Okay, so from 0.001 to 0.0005. What's the half-life? Okay, here. Here. Yeah. Okay, so from here to here is how much? 90 seconds. Equals to 90 seconds. Okay, now you can find another one. Let's try another method. Okay, 0.00, 0.08 here. Okay, here. And to 0.5, I'm going to use red color better. Okay, red color better. Here. To here. And half of 0.0008 is 0.004 here. So from here to here, again, how much? 90, is it? 30, 60, 90. So I put here 0.0008 to 0.0004. Half-life is what? Also 90 seconds. Therefore, first order with respect to what? To I minus, cannot say for the others, okay? Cannot. So from one graph, you can find the RC normally for the initial rate, and of course, find the half-life to show its first order. Now, these are all we do later. Okay. Now last question. Okay. Same one, just on the curve on the graph. Okay. Now this is a bit tricky one. 74. I won't do all, but no time to do all. Okay. 74. Okay. Now this question here. Chromium hexacarbonyl. This chromium hexa means 6. Okay. Here means 6. Carbonyl means carbon monoxide. This is a complex. You learn this in your organic chemistry. Okay, ligand replacement. This will go and kick this out, and so forth, so forth. Don't care about this. So later you learn. 2 separate experiments carried out to study the rate of this reaction. In the first experiment, the ligand Pt2 was in large excess, and this one was measured. Now here they put concentration, but they didn't say what. No. Okay. So here, the first experiment, that means this is the first experiment. You must read carefully, experiment. Okay, first experiment. That means the ligand was in large excess. That means this is the first experiment. What is this? This is your chromium hexacarbonyl. Was measured with time. Okay, this is the first one. Remember, this is the first one. Okay, and the result shown in the graph below. All right. Okay. Okay. Now. In the second experiment, right, this was in large excess. And the concentration here is for what? PR3. Always bomb out with a Y. Wait, no, time is running out. Okay, PR3 concentration. So they changed the concentration here. It means the second graph, you must put with this one here. Okay, right now I've plotted the graph here on this so that make life easier for me and you. Right here, see, that's the same one. See, right now this is the first experiment. This one here, right? This one here, the first experiment. The concentration here is for what? Is for your chromium hexacarbonyl. The second experiment here, right? The concentration is for what? PR3. Now, the first experiment here, right, is a curve. That means this one here must be either first order or what? Second order. Now, for here, if it's a straight line graph, means what? This is what? What order? 0 order. See now? Very nice, isn't it? Okay, now let's go to the question, okay? So the question is here. Plot the graph and blah, blah, blah. Use the graphs to determine the order of with respect to. Okay, right? So here. So show how, in each case, show how you arrive here. Okay, of course, now to show first order, right? The easiest way is to find, use half-life. So here, 0.01 gives to very accurate, okay, to 0.05 is here. Half of this 10 here is 1, 2, 3, 4, 5. Okay, some I can't see that, so 0.005. So you okay, yeah. And you go down here. Remember, you must have 2, right? So it's 660, okay, right now. So it's 600. So from here to here, the half-life 660 seconds. The second half-life, of course, you can do for 5 not here, somewhere here, right? Or you can do from 8. Okay, here. Okay, it's not easy. I say this disturbing. Okay, this disturbing. Okay, I cancel off here. So time is a factor. I don't want to take more of your time. So the first one, of course, is from here to here. Okay, to here. 660 seconds. Now the second one, of course, if I were to draw half of them, okay, half of this one here would be what? 0.0025, which is here. Half of this is 3, so about half be here. Half here, somewhere here, okay, right, somewhere here, okay, right. No, not very good. Is it? I missed the point. So here, here, okay. Sorry about that. So I should have done it earlier. I was too lazy. Okay, draw here, right? You can see it's somewhere down here. Okay, so you can see here, right? Here's it's approximately now this 3. Okay, 3. It's about 660 seconds. See, same, is it? So because of same, half-life is the same. So you conclude here by saying, well, with respect to, remember, this graph here is respect to what? Your chromium hexa. So here, right? So first order, right? Why? Half-life or T half constant. You must tell how much is it. Okay, prove it. Here, 660. Okay, 660 seconds. Do the 2, 1 and 2. The second one is 0 order. 0 order. First order, 0 order. Why? Straight line graph. Okay, straight line graph. Must put down this graph of what? Of concentration of PR3, right? Concentration versus what? Time. Okay, so now you have 2 graphs in one. No, one is a curve, one is a straight line. So you must conclude the final, of course, write the rate equation and calculate the value of the K constant. Use the method, blah blah blah. So of course you put down here, rate, right, is equals to K. Must put a concentration of your chromium carbonyl 6 power 1. Here they don't, can leave it blank actually, right now, but better to satisfy them. Okay, put here 0. Okay, right, and then they ask you to write, okay, and calculate the value for rate constant. Very simple thing, right now. So you can use any one of them. Okay, right. Okay, of course here you to find the rate at this point here, right? You must draw what? I told you, you must find the rate, isn't it? You must extrapolate this one first. Okay, and then use red ink. Okay, you draw the tangent. You can draw out here, doesn't matter. Okay, and then I can't draw it straight. Okay, doesn't matter. Okay, this is called what? This is called your initial rate. Why initial rate? Because you know the concentration of both of them, not okay. So it's important. Initial rate is equals to the slope, and this you must use now here for this part here. Okay, here. Okay, so here to calculate the initial rate, this is the initial rate. Okay, it's a known value. K you don't know, and of course here is how much. Remember, they give you already here. This is your initial concentration, 0.01. Okay, 0.01. Right? Here's 0.01 power 1. Here doesn't matter, isn't it? Whatever amount here doesn't matter. Okay, of course you can put that. Okay, same, right? 0.01, isn't it? Doesn't matter. Okay, 0.01. Why doesn't matter? Because power 0. Here because to 1, isn't it? Right? So K. So here doesn't matter. Right? Because it's 1 here. So what is K equals to? Okay, K rate over the concentration of this one here. Okay, so this one don't come in. So this CO6. Okay, so what's the rate? Okay, the rate is equals to mole per dm cube here per minute or per second. Okay, per second. Okay, per second. Okay, over the constant is mole per dm cube. Now let's check the answer. Okay, let's check the answer here. Is 11 November 43. 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 Okay, let's check here. 11 November 43. 11 November 43. 11 November 43. I should have done this. Sorry about this. 11 November 43. 11 November 43. Okay. All right. Okay, let's see the rate. Okay, see now. Okay, see, first order. All right. Put down here. Draw. See, first order. Okay, we all order. Okay, first order. And with respect to PRD is 0 order. The half-life is about 700 now. Yeah. Okay, this is it. Or see, you must do this one here is better to show the construction lines. You know, the dot 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 like here. See, it's good to show this one. Okay, that's here. No, the dot 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 dot. So this one. Okay, all these are called construction lines. Okay, so it's very important to do that, right? So here, about 660, about 700, doesn't matter, okay, right? So here, because the straight line graph, okay, now remember that here, see now, see, this is a equation. So there's nothing for PR3 here. So remember, so it's per second, see, and the value, of course, there's a range of values that we can do, okay. So here you can see, right here, see now, I did it for you here. Okay, so this cancels off. I put in blue, blue. Okay, so this cancels off. Right behind, s minus 1 per second. See the units, 1 mark, See, so since it's 0 here, you just this. No, well, it means doesn't depend on it. The value of is 1, that's all. Okay, so this is the per second. Okay, this one, all these things here will depend on your slope. They will give allowance for it. Okay, now, okay. So I finished doing this one here. So the next time we'll conclude with the unit tables. Okay, I can see the tables here. The tables are very a lot. Let me show you the tables. Okay, 56. I can show you a few first to well the appetite. And that's the main ones. Tables here. I introduced you before, the tables here. See to reduce the order. Okay, another one 57. All these are tables. Tables here. Okay, 60. The tables, it will become the main focus. See, the tables here. See the tables here. One more. Okay, 61. See, tables here. Okay, so you have to know all the methods. The graph method, okay, of concentration of reagents versus time. They normally don't ask you to change to rate versus concentration. Normally ask you for half-life. Okay, know how to plot the initial rate, right? And from there, come to conclusion what is the rate law or rate equation, and that's how to calculate the K and the units. Okay, right now the table method, I call it the mother of tables, will be the conclusion. You take everything out and put in the table. And from a table, you can actually get your rate equation. And after that the finale will be to produce or predict or Raman-Khan a mechanism for the whole reaction. Okay, guys, thank you, and I'll see you when I see you. Okay, in